Welcome back. In this video, we will be seeing how RNNs are trained. You will see that there are several commonalities between RNNs and let us say CNNs and even ANNs as far as training them is concerned. Of course, as usual you should have a training set, a validation set and a testing set, but that apart, given the particular structure of the RNNs, there are a few subtle things that you need to be aware of in terms of training. So, we will just go through those in this video. There are several even deeper ideas that need to be conveyed that we will not do. Okay. So, in terms of implementation, luckily all the training has been abstracted into the various packages, whether it is MATLAB or whether it is TensorFlow or whether it is PyTorch, etc. But there are a few ideas that will help you later on when you try to train RNNs yourself. So, the two issues that we will be concerned with in this video is first calculating loss in an RNN. There is a mild difference between what happens in an RNN and what happens in a CNN or let us say an ANN. The second issue is what is called backpropagation through time, sometimes simply called BPTT. So, we will be looking at this from a overall view. I will not be doing too deep of mathematics, just a little bit of mathematics we will be doing this, and hopefully this will give you some insight into what actually goes into the code when it tries and trains RNNs. So, first let us look at the loss function for an RNN. So, let us see a simple structure. So, as usual you have some H0 going in, let us say we have unrolled an RNN through many layers. So, let us say the total number of layers is equal to capital T. Why capital T? Because we are thinking of RNN as something that goes through time. So, let us say this is T1 is the first instant, T2 is the second instant, T3 third instant, so on and so forth, and let us say we are going till H capital T. Okay. Now, a question with an RNN usually is where are you going to take out the outputs, and as we saw in the introductory videos, you have several choices. It depends on really what you want. In some cases you will be taking out an output only here, but there are several possibilities where or several cases where you might be interested in let us say finding out outputs at all intermediate layers also. So, just for consistency I will call it y hat, because that is what we have been calling our model or predicted values so far. Okay. Now, when you have multiple predicted values, so let us take the example of let us say having 10 days before is the weather of H0 or temperature of H0 in some city, let us say Chennai. Okay. So, suppose you have that input, you would have the next day's temperature, let us say that is y1 hat, the next day's temperature y2 hat, next day's temperature y3 hat till let us say today's temperature which is yt hat. Now, for each one of them you also have a corresponding ground truth which would be y1, y2, y3, yt. Okay. So, this is the ground truth, and whenever you have a ground truth and a prediction and these two differ, you will have a loss function. Okay. So, not only do you have losses right at the end like we do at let us say with ANNs or CNNs or at least usual architectures of them, you can have possibly, I mean this is not necessary as I had discussed earlier, it could be optional, but suppose you do take out an output, you do have a corresponding loss function. So, the total loss is actually summation of all the intermediate losses through the layers. Okay. Now, in terms of LT itself or the local loss function, you again have many choices, but we have been seeing only two. You can either use cross entropy or you can use least squares depending on what sort of problem it is. Typically, what we have done so far in this course is we have used least squares whenever it was a regression or a numerical output. For example, let us say temperature today, and we have been using cross entropy in case it was a classification issue. For example, you could ask will it rain or not, and in such a case you would probably use something like cross entropy as the loss function. In either case, we will simply say that L is sigma of LT from t equal to 1 to t. So, this is the issue of calculating loss function. It is a simple deviation over or simple correction over all the previous loss functions that we have seen so far. A more important idea or a subtler idea really is that of backpropagation. So, let us look at backprop through time. We will call it BPTT for short. Now, let us see what the subtle issues involved here are. Okay. So, as usual, we will assume this, there is H 1, we start with an H 0, the input here is x 1, H 2, x 2, H 3, x 3, so on and so forth up until H t, x t. And for now, we will assume that we are taking out an output at every single time instant. Okay. Now, let us write the expression for any of this h. We had H t is some g, usually tan h, of some weight matrix multiplying H t minus 1, which we called W H h, plus some weight matrix multiplying x t, which we called W x h, and we also had y t hat was some nonlinearity. Remember, I will call this let us say g star. G need not be the same as g star. That is, we can use a different nonlinearity here and a different nonlinearity here. In fact, in several cases we simply use a linear prediction here. Okay. So, we call this W y h times H t. Okay. So, these are the three sets of matrices. Now, for this video and for the few that follow, just for simplicity, we will use a different notation. We will call this matrix W, we will call this matrix U, and we will call this matrix V. So, that I am going to write H t is G of W H t minus 1 plus U x t, y t hat is some G star of V h t. Okay. Now, the most important thing about an RNN is W, U and V do not change with time. that is another way of saying it is across layers. Okay. So, this is what it actually makes us it possible to train RNNs at least within a reasonable amount of time. So, just to clarify, I have this H1 which was this multiplied by W and this multiplied by U, and this H1 multiplied by V with a nonlinearity of course in all cases gave me a y1 hat. Now, the W here, U here and V here are exactly the same, okay, and you will see how that plays out in when we do back propagation. Okay. So, unlike an ANN where at each layer these W's, U's and V's actually change, in an RNN they are exactly the same. So, we use the same W, U, V for each layer. Okay. Now, how does it helps us of course, because now we have fewer parameters to train, but while doing back propagation we have to be a little bit careful. Okay. So, let us take a specific case. So, remember I want to find out for back prop we need to find del of the loss function. Okay, I am calling it L here, you can use J or L depending on what you are comfortable with. For now I am using L. So, with all the matrices. Now, this means we need to find out del L del W, del L del V and del L del U, because we have 3 matrices as far as RNNs are concerned. Okay. So, this sort of RNN that I have showed you has 3 matrices U, V and W, and I will need to find out del L with respect to each the gradient of L with respect to each of these weights. Okay. Now, remember that L itself is summation of L t, okay. That is, we find out the loss at each of these layers, let us say I will call it L 1, L 2 as I did just a little bit before, and I need to find out del L 1 these 3, del L 2 these 3, del L 3 these 3, and then sum these up, and that will give me del L with respect to any of these weights. Okay. So, let us consider just some one of these. So, let us consider del L 3 del W just to show you what happens. Okay. So, we will consider just one of these local losses and see how we can apply back propagation while using this. Okay. Okay. I will draw a small figure here just to repeat what we had before for clarity. H1, H0, X1, Y1 hat, H2, X2, Y2 hat, H3, X3, Y3 hat, and Y3 hat leads to L3 because Y3 hat in general will be different from Y3. Okay. So, the matrix here involved is V, here U, W, U, W, V, U, W, V. Okay. Now, before we proceed, I am going to make some assumptions on the structure. Okay. I am going to assume that the nonlinearity here, remember Y3 is some nonlinear function which I said was optional of V times H3. We will assume that the nonlinearity here is simply just the linear function, okay, or it is the linear activation function. That is just to make some of our derivations a little bit simpler. You can do it for any case. So, I will assume that Y3 is V times H3 and in general Yt is V times Ht, though that is not going to matter as far as this video is concerned. Okay. Next thing is we will assume that the loss function is the least square loss function. So, let me make it simpler. So, I will call it, let us just deal with L 3, this is half of y 3 minus y 3 hat square. That is just to make our differentiation a little bit easy. Once again you can do this kind of derivation for any loss function. Okay. Now, given these two, what do we need to find out? We want to find out, let me do it here while the figure exists. We want to find out del L 3 del V. Let us say, let us start with that. So, let us say I want del L 3 del V. How would I do it? Like we did before, del L 3 del V is simply del L 3 del y 3 hat del y 3 hat del V. Okay. Now, del L 3 del y 3 hat, you can see here, is simply minus y 3 minus y 3 hat. Okay. So, that is fairly straightforward. Okay. So, you can just simply differentiate this as we did before, even while doing RNNs. Okay. Now, what about del y 3 hat? I should really call it y 3 hat here. Del y 3 hat del V is now H 3. Okay, there is a small catch here, I will mention that here now. I will leave this as an exercise, we will be asking this within this week's exercise. Find out based on the matrix sizes. Remember, L 3 is a scalar, V is a matrix. So, this whole thing is actually a matrix. Okay. Y 3 minus y 3 hat is a vector, H 3 is also a vector. So, please think about which sort of product should come here, or how should you arrange this so that you get a matrix out of this product. So, please think about this, we will be giving this as one of the exercise questions. Regardless, what I will write here is simply that del L 3 del V is equal to y minus y hat times H 3. This simply gives you how much will the loss change suppose I were to change V. That is fairly straightforward. How much will this loss change suppose I were to change V. Now, there is a subtler question here or a harder question here, which is what is del L 3 del W. Why is this a harder question? So, let us first start doing a similar exercise to the one that we have just done. So, suppose I want del L 3 del W, mathematically del L 3 del W will be del L 3 del y 3 hat as we had before. You differentiate this with respect to this, multiplied by del y 3 hat del H 3, because y 3 hat depends directly on H 3, multiplied by del H 3 del W. Okay. I hope this is clear. We just saw that del L 3 del y 3 hat is simply minus y 3 minus y 3 hat. That should be straightforward. Similarly, if you come down here, what is del y 3 hat del H 3? Okay, please notice this, this is simply V. Now, what about del H 3 del W? Del H 3 del W, for that we need to know what the expression for H 3 is. H 3, recall, was g of some nonlinearity, usually tan h, of, let us see this here, H 3 is W times H 2 plus U times X 3. Just to recall, you can see this. Okay. We want del H 3 del W. So, for simplification, let us call this Z 3. Okay. So, this is therefore G of Z 3, very similar to what we had for ANNs. H is G times G of Z, or activation is G of Z, it is very similar. So, if you have that, then this becomes G prime Z 3, that is del H 3 del Z multiplied by del Z 3 del W. Okay. Okay. Let us continue in the same vein. So, this gives us G prime of Z 3 multiplied by del Z 3 del W. So, now let us look at this. What is del Z 3 del W? Okay. Obviously, none of these terms depend on del W. So, this derivative goes to 0. You have this derivative, this should give us H 2, which is straightforward, plus there is one more term which is W times del H 2 del W. Now, why does this term exist? Okay. Is this 0 or is this non-zero? This is non-zero because notice that H 2 itself depends on W. Okay. Just like H 3 depended on W, H 2 also depended on W, depends on W because it is the same W throughout. This is the catch with back propagation through time. Unlike ANNs, where you would have a W 1 here and a W 2 there, in the RNN it is the same W everywhere. So that you cannot find this out independent of del H 2 del W. Okay. So, in summary, you have del H 3 del W equal to G prime Z 3 H 2 plus W del H 2 del W. Now, suppose you want del H 2 del W, you will have to go back again, and this is why it is called back propagation through time. Okay. So, you have G prime of Z 2 H 1 plus W times del H 1 del W, etc. Okay. So, whenever you want to find out del L 3 with respect to del W, or gradient of L 3 with respect to W, you will first come down here. Okay. You have these two terms sitting there, but this is actually a more complex term. It is G prime Z 3 times H 2 plus W times del H 2 del W, and in order to calculate del H 2 del W, you will have to go back, okay, and so on and so forth. Okay. So, similarly, you will, whenever you want to find out, let us say del L T del W, it will involve all the gradients before. Okay. So, you will have these repeated sort of recursive additions sitting there, and there are very clever ways of writing these codes, as people have already done within TensorFlow, etc. Okay. So, we have now seen two terms, we have seen del L 3 del W, we have also seen del L 3 del V, which was straightforward. Finally, let us look at del L 3 del U. Okay. So, once again the same thing, the first two terms will be the same, del L 3 del U is equal to del L 3 del y 3 hat multiplied by del y 3 hat del H 3 multiplied by del H 3 del U. Okay. Now, this if anything is mildly trickier than the previous one. This is V. Now, if you notice this figure, when I was doing del L 3 del W, you could see that this depends on this depends on this depends on W, okay, and through that W it comes through here. Now, it looks like this should go through when we take a gradient with respect to u, that it should go through straightforward, but there is some subtlety there too. So, let us calculate this term. So, suppose I want del h 3 del u, remember this is del by del u of h 3 is g of z 3. So, this is del g z 3 with respect to z 3 and del z 3 del u. Okay. This is g prime z 3 times z 3, we have it here right here in front of us. Okay. So, what is del u of that? What remains is x 3 plus u times you have del u of this term here w times h 2. Okay. Now, it might seem like this term is of course 0 because h 3 x 3 does not depend on u at all. Now, what about this term? This term is, like I said, a little bit subtle. Okay. So, if I look at the term del of w h 2 with respect to del u, this can be written as w del h 2 del u plus this term is 0, but this term is not 0 because this is w times g of z 2 del g of z 2 del u, which in turn is w times g prime z 2 times del z 2 del u, and this is not 0. Why is that? Because z 2 is equal to w times h 1 plus u times x 2 and it depends on u. Okay. So, this is very similar to what we did with this there is a recursion there. Okay. So, in all three cases, well, in both the cases, in the case of w as well as u, you have a dependency which is actually sitting there, which will make you back propagate through time. You cannot simply find out the gradient of L 3 with respect to w or u without finding out gradient of L 3 with respect to this throughout time, and this is why sophisticated expressions exist. And when we look at in the next couple of videos, when we look at deep RNNs, you will see that this issue can actually become a little bit more complicated, which is why TensorFlow, for example, has a full graph. So, all these dependencies are resolved in terms of graphs by using automatic differentiation, and backpropagation uses automatic differentiation one sort or the other. So, that is it for backpropagation through time. The basic idea for you was to see that training can be a little bit more complex. In practice, unless you are writing some new architectures by yourself or entirely new architectures, something that nobody has ever thought of, you will not really be doing this by hand ever. But this is slightly important for you to see or at least get an intuition of what is happening, and as well as to see the next video where we will be dealing with vanishing or exploding gradients. Thank you.